Good morning, and once again welcome to my YouTube channel, Maths with Ease by Mr. Kamotho. And in this video I want us to introduce a very important topic called graph 9, and it's the one that is going to introduce us to the calculations of gradients of curves at specific points. As we have heard in the previous slide that the gradient of a curve is equals to the gradient of the tangent to the curve at the point of contact. And we all know that the tangent is a line that touches a curve at only one point. For example, if you may want to consider a tangent of this curve at point A, it is going to be that very straight line. That is going to be the tangent of the curve at this very point. So the gradient of this straight line, which becomes now the tangent, is equals to the gradient of the curve at point A, since point A is the point of contact. Now, how do we generally calculate the gradient? We have considered the equation of the graph of y is equals to x squared. And the graph of y is equals to x squared. So this graph from here all the way is equals to y is equals to x squared. Every point on the curve is satisfying this equation. And I would want us to generally consider point A and point B. What are the coordinates of point A? Of course, you can see the x value of point A is actually x. So point A has coordinate x. And since y is always equals to x squared, then the y value of point A becomes that x squared. So x squared. That is the coordinates of point A. This one. The coordinates here is x squared. What are the coordinates of point B? As you can see, from A moving horizontally to the right, we get a very small change. This one is called delta x, which is talking about a very small change. And the x coordinates at point B is this x plus this very small change, which is x plus delta x rather. That is now the x coordinates of point B. So x plus delta x, it's actually here, x plus delta x, and the y coordinates is whatever the value of x is squared, because y is always equals to x squared. The value of y at this point is the value of x now squared. So we have x plus delta x squared. We know how to calculate the gradient from the first principle. It is always rise over run. It is always the change in the vertical dimension over the change in the horizontal dimension. So it is generally known as gradient is always rise over run. And we can always talk about sometimes the change in y. It is always called the change in y all over the change in x. You can also say so. Now, what is the change in y and what is the change in x? What is the rise and what is the run? So the gradient of any straight line that is joining A and B, for example, the line segment AB, is going to be x, the difference between x coordinates, x plus delta x squared minus x squared all over the change in x, which is x plus delta x minus now this x. And we would want to open up this bracket, which gives us the gradient now becomes x squared plus, if you know how to open the bracket, x dx plus another x dx, which gives us 2x dx plus dx squared. We have now opened this bracket, and if you like, you can open it separately. You will always get this. Now, obviously, the whole of this is subtracting x squared. Everything over, when we evaluate now the denominator, x minus x cancel out, and we are left with delta x, or the change in x. Now, let us now talk about the gradient of the line segment AB, which is now the simplification of this. X squared minus x squared becomes just that. And we have 2x dx plus dx squared, everything over dx. And you realize that delta x is common in the two terms of the numerator, so we get it outside. Delta x into the bracket, we have 2x plus delta x, because this one squared divided by delta x is simply delta x all over delta x, and this cancels out. Delta x and delta x cancel out, so we are having the gradient of AB. Remember, we are looking for the gradient of line segment AB, line segment AB, because this is how we look for the gradient of straight lines. And this one leaves us with the gradient as 2x plus delta x. That is not all. We were never interested in the gradient of line segment AB. We were interested in the gradient of the tangent of the curve at point A. And as you can see, if we changed position of point B to B1, we can already see that it has come closer to point A. And that means now the error is smaller. If we continue changing now from position B1 to B2, you can see the line segment AB2 is a straight line that is joining A and B2, and the error, as you can see, it is there but significantly reduced. How do we do this? So if we continue to push B closer to A, the delta x continues to decrease. Delta x was from here to here. When we came to B1, delta x was from here to here. When we came to the point B2, delta x is now from here to here, reduced. If we can even find another point B3, delta x is now from here to here. But eventually, when the point B comes to the same position with point A, and that is now how we form a tangent, the delta x will be reduced significantly. So as we can see, we had a big right angle triangle, A, B, all the way to here, and that is how we started rise over run. But as B approaches A, the delta x continues to decrease. And once B is on A, the delta x is actually 0. So we should understand that fact. Therefore, and this is NB, as delta x approaches 0, the gradient of the tangent, we can call it AB, is equals to 2x plus 0, which is 2x. Incidentally, when B is upon A, when B is upon A, then AB is the tangent of the curve at A. the tangent to the curve at A. And therefore, the gradient of the curve at point A is actually 2x. And that is how we explain the gradient of a curve using first principle. I hope it has sunk, and I hope this topic is well introduced. We shall continue answering some other question and explaining other aspect of gradient. Let us meet in the next video. Thank you.